Here we go, section 6. Work, energy, and power, all of which, by the way, are scalars. So it's a nice little break for you. You've probably noticed scalar arithmetic is simpler than vector arithmetic. All of these things are just numbers without components or anything like that. Not that you've seen the last of vectors, but let's consider, I'm dragging a box across the table, okay? And I've got a string taped to the box, and I'm pulling on it. Now, basically the idea of work is that it's how hard I pull times how far I pull. Just in the everyday, ordinary meaning of the word work, most people would agree that if I have to pull harder, that's more work, okay? If I'm moving a refrigerator, it's more work than if I'm moving this little box full of plastic gloves. And also, all else being equal, also more distance, more work. If I have to take a refrigerator to the other end of the building, that's more work than just moving it across the room. So basic idea, work equals force times distance. How hard do I pull times how far do I pull? But there is, isn't there always, there is a complication. Let's say I don't know, I've got a wagon that I'm taking down the hall here. I'm at the college. Practically nobody else is. This place is pretty empty, but let's say one of the few people who are here decides they want to help. So as we're taking the wagon down the hall, this person is pressing down vertically on the wagon like that. Now, this is not helpful. Only forces along the direction of motion are thought of as doing work. Forces across the direction of motion don't. Well, what if you've got a force at an angle, like the way this one is drawn here? Well, it can be thought of as the resultant of its x and y components. Those two forces taken together are equivalent in every way to having this force at an angle act. This vertical component is like my misguided friend that I was talking about a minute ago. A force across the direction of motion does not help propel the wagon down the hallway. It doesn't do me any good at all. So only the parallel component is thought of as doing any work. And hypotenuse times cosine equals the adjacent side. So the better way to define, saying just force times distance is kind of misleading. The more accurate way of defining work is to say it's the component of the force along the direction of motion times the distance, or just simply the force times the distance times the cosine of the angle in between. A unit to measure work in, well, force is measured in newtons, distance is measured in meters, work would be measured in newtons times meters. As is often the case, not always, but as is often the case, this combination of units is given a name of its own, and as is often the case, it's somebody's name. You can look up James Prescott Joule if you're interested in who he is, but all you really need to know is that they named this unit after him. Some examples to illustrate the idea. Let's say you carry a bucket of water 100 meters. Question is, how much work do you do on it? Pause here and unpause, and I'll tell you, you worked out, you thought about it yourself, right? No cheating. The answer is 0. This is why. bucket. I'm rather proud of my buckets, actually. I can't draw a human, well, I got the handle kind of crooked. I was about to say I can't draw human beings to save my life, but I'm pretty good at buckets. But it looks like I need to work on the handle a little more. Anyhow, the question says you're carrying it over level land. We're using the letter S for the displacement. S would be measured in meters. Earlier in the course, I'd have been using delta X for displacement. Why the change in notation? Well, maybe it's more trouble than it's worth, but the idea is if you call it delta X, that means you're moving along an X-axis. With this, if you look ahead to some of the examples that are coming up, the thing isn't always moving along a straight line. And so delta X didn't seem entirely appropriate, and we changed to a different letter. And like I said, maybe that's more confusion than it's worth, but well, it's too late now, it's all printed up. F for force. As you hold on to the handle of this bucket, you're pulling upward. The theta in Fs cosine theta is the angle that these two things make if you stick them together. Force that way, displacement that way. That's 90 degrees. That looks, okay, that's better. Like I said a couple of minutes ago, only the component of the force along the direction of motion is thought of as doing any work. Well, if the thing's moving horizontally and the force is vertical, it has no component along the direction of motion. Now, anybody who's ever carried water can tell you it's a lot of work, but not in this sense of the word, okay? You'd be all tired out if you just stood in one spot for a while, holding up a bucket of water. But the bucket moves because of Newton's first law, okay? You do have to do a small amount of work in the beginning. When you take your first step, if somebody was watching you extremely closely, as you began to move, your arm would swing behind you a little bit. And so there'd be briefly a forward component of the force to get the bucket going. Likewise, at the other end, when you stop, your arm would briefly swing out in front of you a little bit to make the bucket, so you'd have a back, a force toward the back to stop the thing from moving. But aside from those endpoints, anywhere in between, the bucket is moving because of Newton's first law. It's an object in motion, and so it remains in motion because there's nothing to stop it. All you're doing is holding it up off the ground so it doesn't rub. To look at this from I never did write down the answer, did I? I think you probably kind of gathered by now. The answer is that the work is 0. To look at it from another point of view, when I get a little further down the page, it turns out that when work is done, it's some sort of a transfer of energy. I haven't quite defined the word energy yet. That's coming up in a few minutes, but to kind of give you a little preview, if you add energy to something, that's positive work. If you take energy away from it, that's negative work, okay? Now, work, energy, and power, as I said, they're all scalars. You're probably used to thinking of plus and minus signs as being directions, but these things have no direction. Rather, plus and minus is just, basically it means add or subtract, okay? Um, it's like how much money you have in your checking account, which is sort of, energy means stored up work. The money in your checking account is sort of another kind of stored up work. You have to get money, you have to do work to get the money. Then after that, you can get someone else to do work for you by giving them the money. You can walk into a restaurant and say, cook my dinner. And if you're making a deposit into the checking account, there's a plus sign involved because you're adding to the balance. And if you make a withdrawal, you write a check or whatever, there's a minus sign involved because you're subtracting from the balance. And it's the same thing with work. When you add to the amount of energy it has, that's positive work. When you subtract from the amount of energy it has, that's negative work. So that's what the plus and minus signs are all about. That it's not a direction. If the angle between the force and the displacement is 0 through 89 degrees, then you've got a component in the direction that it's moving, which helps it go along. So that's going to be doing positive work. If the angle is 91 through 180 degrees, then the force is against you. It's pulling against the motion of the object instead of helping it go along. That's going to do negative work. When it's 90 degrees, neither one is true. That's going to neither add or remove energy, and so no work is done. So back over here. And I've kind of already covered the next few sentences there. Although it has no direction, work can be positive or negative. Here we see a force that points in exactly the opposite direction that the thing is moving. Friction, for example, would behave that way. Friction isn't the only thing that would behave that way, but this could be the force of friction as the thing slides along. With the displacement and the force having exactly opposite directions, you'd be taking the cosine of 180 degrees, which is equal to -1. So positive work energy is added, negative work energy is removed. Energy means the ability to do work. In other words, if something is capable of doing work, it possesses energy. Since the energy tells you how much work something could do, that would be measured in units of work. So energy is measured in joules just like work is. There are a number of different ways that something would be able to do work. One of these is because of its position. Okay, if I'm going to kind of jiggle around while I hold the camera in my hand, but I've got this box. And if I push the box across the table, I've done work. Now, if I had, what can I use for a weight? If I had a piece of string, which I'm not going to go bother to find a piece of, I do have string here, but I'm not going to get it. But just imagine that I've got a piece of string taped to one end of the box, and it goes over the edge, and hanging off the edge of the table over here, I've got this weight, which happens to be a stapler. That stapler is capable of doing work, okay? I just got done saying if I push the box along like that with my finger, force times the distance I push it, I've done some work. Well, if I let go of the stapler, it's going to do exactly the same thing I just did with my finger. The string will pull the box across the table as the stapler goes down. So due to the fact that it's elevated, the stapler is capable of doing work. How much work could it do? We'll never find out if that doesn't focus. I'm not quite sure why that works, but it does. Well, the stapler can exert, work is force times distance. If the stapler goes right straight down, the cosine factor is equal to 1 because the force and the direction of motion are parallel. So force times distance, newtons times meters. The stapler can exert a force equal to its weight, mg. And the stapler can move a distance h, where h stands for height. How far was it off the floor? So force times distance, mg times h, is how much work an elevated object is capable of doing. We call that potential energy, or gravitational potential energy to be precise, because there are other kinds of potential energy. This is the only one that we'll get to in this course. If you come back for Physics 122, we'll talk about electrical potential energy. Another way that something would be capable of doing work is if it's in motion. The work that a moving object could do is called its kinetic energy. And, it doesn't take that long to prove this, but it takes a couple of minutes, and I'll bet you just assume that I've got an honest face, right? So it turns out, as a result of a fairly straightforward calculation, you can show that the work a moving object could do is 1/2 mv squared, where m is the object's mass and v stands for velocity. So for an example of this, consider a hammer, which is approaching a nail at about 45 miles an hour. Because of the fact that the hammer is in motion, that makes it capable of doing work. Just like being elevated made the stapler capable of doing work. When the hammer collides with the nail, there's going to be a force. If you've ever gotten your thumb in between, you've been painfully aware of that fact. And as that force acts on the nail is going to move some distance down into the board. So you've got a force that acts through a distance. Work is being done. What makes the hammer capable of doing work is the fact that it was in motion. These two types of energy are the two mechanical forms that energy can take on. And since for the time being we're looking at the branch of physics that's called mechanics, those will be the ones that get all the attention. But there are plenty of non-mechanical forms of energy also. Chemical energy, for example. If you put a little bit of gasoline into the cylinder of an engine, that gasoline can undergo a chemical reaction that makes it capable of doing work. The gasoline molecules can react with the oxygen that's in there in a way that makes a lot of pressure build up inside the cylinder, and that pushes the piston down the cylinder. So you've got a force acting through a distance on that piston. Work is being done. What makes gasoline capable of doing work is the chemical reaction it can go through. Heat is a kind of energy. You can build a fire under a steam engine, and it will exert a force through a distance. And there are other examples also, but those are all non-mechanical types of energy. So we come to another problem for you to consider. Pause the recording and see if you come up with 500. And now I'll go over it in case you couldn't get 500. Actually, I can probably fit it right in there. So this is almost a plug and chug kind of thing. Just throw the number, you got the formula sitting there, 1/2 mv squared. just see, what does it ask for again? Helps if you read the question. Okay, 1,200 joules of work. If 1,200 joules of work was done accelerating this bullet, that means in the end, the bullet had 1,200 or 1,250 joules of kinetic energy. Energy is just stored up work. Work is done transferring or transforming energy either from one place to another or one form to another. So saying work was done on the bullet, saying energy got added to the bullet, same thing. In kinetic energy equals 1/2 mv squared. (1,250 joules is the amount of kinetic energy that the bullet had in the end. So you need to realize that, and the only other thing you need to realize is that a joule is based on kilogram, like anything in the SI system. Joules are based on kilograms, not grams. So you have to take the 10 grams and convert that to kilograms by moving the decimal 3 places. And then there are considerably more elaborate ways of coming up with the same answer. Some of you may have tried something else that was not incorrect. Multiply both sides by 2, divide both sides by the 0.01, and then take the square root. Comes out 500 meters per second. I've seen people on tests where I gave them some sort of similar question say, well, let's see, 1,250 joules of work. That work is force times distance. So yeah, in this case, there's no distance given. But if there was, then they use that to figure out the force. And once you've got the force, you put it in F equals ma. And then once you got the acceleration, you can figure out, yeah, that's a lot longer than this. But here you couldn't do it in this one anyhow because you don't have a distance. But there often are other alternative ways of solving problems. Just sometimes they aren't very good ways of doing it because it takes you all day. Well, let's see what's over here next. Conservation of energy. Conservation means to keep things the same. Conservationists want to keep the swamps the same. People who are politically conservative don't want the country to change. And here we're talking about how the total energy in some system doesn't change. By a system, I just mean a collection of objects. It might be just one object you're talking about, or it might be, several. Total energy would be potential plus kinetic plus heat plus chemical plus every other kind of energy you can think of. If you look at it at 2 different times, before and after, well, the energy might have changed from one kind of energy into another. If the system contains multiple objects, the energy might have moved from one object into a different one. But once you add everything up, for every object, every kind of energy, the total has to be the same before as it is after. Another way you hear it phrased sometimes is just to say energy can't be created or destroyed. It can move around, it can change form, but the same total amount always has to be there. Well, let's, this general idea, conservation of energy, is kind of wide-ranging and philosophically significant. It's one of the basic principles that describes how our universe works. But as far as turning it into a useful problem-solving tool, let's rephrase it in a form that's called the work-energy theorem. Because energy has to be conserved, if you look at some object or some system of objects, its original energy, again, 2 times, 2 points in time, before and after, like in the magazine advertisements for the weight loss products, you have the before picture with the unhappy looking person that's sticking their belly out as far as they can, and then the after picture with the happy looking person who's sucking their belly in as much as they can. 2 different times, before and after. The energy in the original picture plus the energy that's added in between has to equal the energy in the final picture, okay? What you start with plus what you add has to equal what you end up with, because energy can't just pop up out of nowhere and it can't just disappear. Well, saying energy was added to something means the same thing as saying that work was done on it. So original energy plus work done equals final energy, where I'm using the word energy here in a sort of a narrow sense to mean the mechanical energy, kinetic plus potential. Subtle little point, NC stands for non-conservative. Yeah, let's just make a long story short here and say that for our purposes, this means work done by forces other than gravity. If you include the work done by gravity in this term here, well, the change in potential energy is the work done by gravity. If you also include work done by gravity here, you're counting it twice. So, you can, there are better ways of explaining that are also longer and more complicated. But as far as what you need to keep in mind, non-gravitational forces is what maybe I should have had NG for non-gravitational. Anyhow, initial plus work equals final. And I'm going to run through an example, and then you're going to do one, and then I'm going to do one, and then you're going to do one. Or if you're feeling really ambitious and confident, you can try doing all 4 of them on your own before I run through them on the recording here. But what I sort of intended was for the first one to be kind of sort of a pattern you could imitate in the second one, and the third one to be kind of like the fourth one, to give you some help with that. And now you can see them better. A little crooked. Almost off the edge of the picture. Okay, that just barely shows up, that, except that got to be a little further back so it, oh, okay. And you're all sitting there going, stop messing with the camera and just get to the point. So, a box sliding down the ramp. It starts out elevated 3 meters above where it's going to end up. It gives the mass, it tells you it starts at rest, and it tells you how much work is done by friction on the way down. 50 joules lost to friction, that would be the W, the work done by forces other than gravity. So how fast is it going at the bottom? Anytime you use energy methods to solve a problem, you can think of, the thing you start with, the jumping off point, is the work energy theorem, like it says farther up the page. Kinetic plus potential initial plus the work done, not the total work done, which would include the work done by gravity, but the work done by any non-conservative forces such as friction. Now, it's not always necessary to actually write it out in that much detail, because more than one of the terms that I've written here is zero, okay? And if you can spot that right away, then you don't have to be quite so elaborate about what you write down. But I'm trying to be step by step and methodical here and dot all my I's and cross all my T's. And so if it's not immediately obvious to you that you shouldn't bother to write something down because it's zero, then always start with this and then fill things into it. The initial kinetic energy is one of the things that's zero, because the picture says that the block starts at rest. So kinetic energy is 1/2 mv squared, and v is equal to 0. Or without even getting into the formula, kinetic energy is the energy of an object's motion, and if it's not moving, you don't have any of that. The block is elevated in the beginning, so it's got some potential energy. I for initial. The work would be the work done by friction. Don't forget the minus sign. Remember how I was saying earlier that work is positive when energy is added, work is negative when energy is removed? Well, friction always removes energy, okay? Friction always opposes motion. And therefore, anytime, there's that cosine of theta factor in the formula for work, force times distance times the cosine of the angle in between. If it's friction, the angle will always be 180 degrees, because friction always opposes motion. Whichever way something moves, friction points the other way. So minus sign, because energy is being lost. Kinetic energy is 1/2 mv squared. And the final energy is that's what we're trying to solve for. Final potential energy, well, in the end, the box has gotten to the bottom of the ramp. It's no longer elevated. So mgh, where h is equal to 0, there's no potential energy. It's not elevated anymore. So potential energy that it starts with minus what's lost to friction is equal to the kinetic energy it's got when it gets to the bottom. What friction does is it takes mechanical energy and converts it into heat, okay? Energy always has to be conserved in the large, in the broader sense of the word energy. Energy can't just disappear. Where did the energy go? 50 joules was converted into thermal energy. The bottom of the box and the top of the ramp will be a little warmer after the box has slid down than they were before. Fill in the numbers. For mgh, first of all, the mass of the box is 5 kilograms. Gravity, as usual, is 9.8 meters per second, and the original height was 3 meters. And we've got minus the 50. 1/2 mv squared. 5 kilograms again for the mass. Final velocity is the unknown I'm trying to find. That times that times that, 147. Half of 5 is 2.5. That minus that is 97. And then divide by 2.5, followed by take the square root. And I should get out of the way, but that's how fast it's going when it gets to the bottom of the ramp. So you try this one. Number 3. And I'm assuming that here's where you've unpaused it after trying yourself. So get a spot I can write, and we'll go through this one. So again, if it's not immediately obvious to you what's equal to 0 and what isn't, then start by just writing out the whole thing. Being methodical and step-by-step-ish, if that's a word, is usually a good way to keep from getting messed up. Work energy theorem. What you start with plus what you add equals what you end up with. This time, work is 0. No work other than gravity. I think I need to aim the camera a little bit higher. There. You know what I need to do is I need to set it back further. I didn't need it higher. I should have left that alone. There. Okay. In the absence of any non-conservative forces, the mechanical energy is conserved. See how the terminology works? The initial energy equals the final energy if there aren't any forces adding or removing energy in between. So, because it's frictionless, the potential energy that you start with turns into kinetic energy by the time the book reaches the floor. So kinetic energy is 0 because it starts at rest. And the final energy is 0. Focus, thank you. Because it's no longer elevated. That part's the same as the one that I did over to the left here. So really If I was just doing this myself on the back of some old envelope, I would just start out by writing down this. As the book, notice it's a ball. Okay, as the ball falls, the potential energy that it starts with, it's turned into kinetic energy. As time passes, it's lower and lower, so it's got less potential energy. As time passes, it's moving faster and faster, so it's got more kinetic energy. The one kind of energy is changing into the other kind of energy, but the same total amount is always there all the way down. The question didn't give us the ball's mass. Not to worry. It drops out. Divide both sides by m and it's gone. So to solve for V final, multiply both sides by 2 and then take the square root. .8 for G, 2.5 for the distance that it falls. This thing hits the street at 7 meters per second. More examples. Now, that one that I just went through, number 3, you might look at that and say to yourself, well, we could have done that one the first week. All you have to do is say V final squared equals V initial squared plus 2a delta x. And you're right. It could have been done that way. And maybe that might even be the easiest way to do it, although this isn't really that much harder, but work and energy methods in principle don't let you do anything you couldn't have done with other methods from earlier in the course. But in practice, it's nice to have alternatives because sometimes one alternative is easier, sometimes a different alternative is the better way to do something. So this one where you drop the ball, yeah, it's at least as easy using methods from earlier in the course. But, you know, like I said, it's not so bad this way. This next one, on the other hand, in principle, could be done using F equals ma and things from earlier. In practice, it would be, at best, a lot harder than it needs to be. Might even be in trouble. Well, anyhow, here's the situation. You're driving, this is like a cross-sectional view of the landscape. This is seen from the side. So you're out driving around somewhere by the seashore, apparently. And point A is right down at sea level, which is kind of a bad way to build a road because it'll flood when the tide comes in. But, well, we don't need to get into that. Just point A is right there, and just so happens that's where you run out of gas. Well, you know, there's a gas station over here at point B, 3/4 of a kilometer away, roughly half a mile, and you just barely make it, as in you coast to a stop next to the gas pump. So if that's how things work out, and if the average friction force, you know, taking into, well, I mean, we didn't really get into how to calculate air drag or anything like that, but if we had, let's say it's 450 newtons that would have been acting on your car. Given all of that, how high is the gas station above sea level? In other words, in the potential energy, what's H final going to be? Well, if you try and do this with F equals ma and other related equations from earlier in the course, the problem is that the acceleration is not constant. You go up the hill and you're losing speed, and you come down the other side and you're gaining speed, and you go up along here and you're losing speed again. As the angle of the road continuously changes, your acceleration continuously changes. And so if it's not a constant number, what do you do for A in F equals ma? Well, the answer is what you have to do is take the whole 3/4 of a kilometer and you have to divide it up into lots of little pieces, each of which is small enough that the acceleration is pretty much constant. You can use that kind of thinking to set up a differential equation, which, why don't I just stop right there? Because instead of getting involved with that kind of nonsense, if you use energy methods, you can solve this in just a few lines of 9th grade algebra, okay? So, like I said, alternatives. Sometimes doing it a different way might be at least as good, but sometimes not. So I'm going to pick you up and set you here at the other end of the table. Just a few moments with an eraser. Kinetic energy plus potential energy initial plus work done by forces other than gravity equals kinetic plus potential final. Kinetic energy is 1/2 mv squared. I should look at the monitor once in a while. Yeah, make sure everything's going all right. Potential energy is 0 because, initial here means point A. And point A is where you were right down at sea level. Work. Well, unlike this one that I did earlier where the box was sliding down the ramp, you're not given a number for the work. You're given a number for how much force was acting. People sometimes get force and work mixed up with each other. Don't do that. Force is newtons, work is newtons times meters. Or when it's friction you're talking about, negative newtons times meters. Okay, and I've already said this a couple of times before, but I suppose saying something too much beats saying it too little. So if you consider a short section of that 3/4 of a kilometer that the car goes. Here I've got it going downhill, but it's the same principle anywhere else. That's the displacement vector. Okay, that's how far the car moved. And this is the force vector, the force of friction. Work is defined as force times distance times the cosine of the angle in between. Anytime that it's friction, the angle will be 180 degrees because friction always opposes motion. If you take that arrow and put it together with that arrow, kind of like this, it makes a 180-degree angle. So force times distance times the cosine of the angle in between. The cosine gives you the minus sign. Work done by friction is always negative because friction takes energy away. Now that I've beaten that to death, over here on the other side, the final kinetic energy is 0. Because you coast to a stop. When you stop, you've got no kinetic energy. H final is the unknown thing that the question asked us to determine. Okay, so we've got 1/2 mv squared minus fs equals mgh. Is, you know, when the dust settles, that's what we've got to fill numbers into. Mass of the car, 1,000 kilograms. Initial velocity, 30 meters per second. Something in the low 60s of miles per hour, a little over the speed limit maybe. So 1/2 mv squared minus the force times the distance. The force, 450 newtons. Joule is a Newton meter, not a Newton kilometer. Convert to meters. Quarters of kilometer, 750 meters. Over on the other side, mgh. Right small, I can squeeze that in. Mass of the car, 1,000 kilograms. Gravitational acceleration, 9.8. H final is our unknown. Oh, some big ugly numbers. I'll write them down in case anybody needs to check their arithmetic. Like, you know, classic example of them. Somebody probably forgot to square the velocity. You know, people do stuff like that, and I knock off half a point on a quiz. But if you remembered to square the 30, this should be 450,000 that times that is 337,500. Over here you've got 9,800 times H. And so that minus that is 112, 500. Eleven and a half meters above sea level, like 35 feet or something like that. I was much younger than I am now, my grandparents lived on top of a hill. It was a really good hill for sliding down in the wintertime. I don't know if it was 9 meters high. Might have been. Actually kind of sounds about right. But nope, got to do it again. Did it too fast. Focus on that. And then, oh, come on. All right, well, it's a little on the fuzzy side. No, actually, it's a lot. Yeah, I guess you can read that even though it's not pretty. So here we have a child on a sled up near the top of this hill. And at the base of the hill, there's this level pasture down here. Today, it's all woods. You'd never guess anybody'd ever slid down through there, but 50 years ago, it was a really, or actually 55 years ago. Anyhow, 50 years ago, it was a really good place to slide. So here's this kid up here, kind of just holding onto a weed that's sticking out of the snow. And when he's ready to go, he just lets go of the weed and, you know, some little tree that's starting to grow and slides away. So begins at rest, slides until he comes to rest again. And then you get off the sled and you climb back up the hill and you do it over again. And so the question is, how far do you go? Given the friction force would, you know, change a little bit with the changing angle of the ground. You know, the normal force would be a little different on the hill than it is over here, but if it averages out around 115 newtons. Anyhow, pause here. And now go over it. We will as soon as there it is, yep. Kinetic plus potential. Initial. Work done. Kinetic plus potential. Final. You start at rest. Nobody pushed you. You just let go and began to slide. So starts out at rest. In the end, you coast until you stop. There's no kinetic energy over here either. And in the end, you're no longer elevated, so there's no potential energy. The final height is zero, the final potential energy is zero. So basically, all that's non-zero is that you start out with some potential energy because you're elevated. That energy is used as work done against friction as you slide along, and in the end, you've got none. When you climb back up, you replenish the potential energy. Where does that come from? Chemical energy that was stored in your muscles. Came originally from something you ate. So original potential energy, mgh. The work just like I explained in the previous example, the one with the car that ran out of gas, work done by friction is minus F times S, the minus sign coming from the cosine factor, 180 degrees. So I can add the work term to both sides. S is the distance. How far did you slide? To solve for S, I'll divide by F. Fill in the numbers. Total mass, child plus sled, 65 kilograms. G is 9.8. The initial height, 9 meters. And the force, the friction force, 115 newtons. So for anybody who needs to check their arithmetic, that times that times that is 5,733. Divide that by 115. 49.9 meters. Time to turn the page. I'll lower that. Another example. Hockey puck sliding across the floor. When it first leaves the puck, it's going 15 meters per second. I don't know what it's sliding across, but it goes a pretty long distance before it stops. So it's probably something kind of slippery. Anyhow, find those things. Pause here. And now unpause. Of course, if you got the right answer, even if you got the right answers, you might still want to hear what I've got to say about it. I might say something illuminating, or maybe not if you're short on time. Anyhow, I should make a spot to write. And as I probably say every week, if there's some of these that you can't do without looking at how I do it, after you've seen me do it, it's a really good idea to stop the recording and try again and see if you can do it yourself now. Because in the end, it's not about you sitting there looking at me going, oh yeah, that makes sense. I see how we did that. It's can you do it is what's gonna determine how you do in this course. So number 5. So once again, writing out the whole work energy theorem in glorious detail, just as sort of a general jumping off point, even though half the stuff in it is actually equal to 0. The stuff that we could dispense with this, well, actually, it's not the only thing we can dispense with, but one thing we can dispense with, potential energy terms. This puck is sliding across a level surface. So therefore, H initial is 0, H final is 0, or even if you for some reason want to measure the height from some other level, it's still true that H initial equals H final, and so the two terms are going to cancel out. So because it's a level surface, the potential energy terms cancel out. In addition, should have left myself a little more space to write, but the final kinetic energy is also 0. There, squeezed it in up there. In the end, the puck comes to rest. Kinetic energy is the energy of something's motion, and if it's not moving, it doesn't have that. So 3 out of 5 terms I didn't really need to bother writing down in the first place. What's non-zero is that. Part A asks for the work. Well, it's just going to be equal to 1/2 mv squared. Actually, the negative, to be precise. Not too surprisingly, the work done by friction is going to come out negative. So I subtract that from both sides. It gives me that. And stick in the numbers. 0.17. It's originally going 15 meters per second. So the kinetic energy that it started with got used up as work done against friction. So the work done by friction is equal to the kinetic, well, actually the negative of the kinetic energy it started with. Part B. How much force did friction exert as it was sliding along? Well, the basic idea here is to oversimplify a little bit, just to kind of illustrate the general idea. Work is force times distance. We know the work, we know the distance, we can get the force. In a little more detail, there's the general definition for work from part A. You know that the work is 19.1 joules. The friction force, big F or little f, whatever kind of F you want to use for it, that's the unknown I'm trying to determine. Anytime it's friction, theta is 180 degrees. Friction always opposes motion. The cosine of 180 degrees is -1, so the minus signs cancel each other. 80 meters. And then divide both sides by 80 and you get the answer. Work is in Newton meters. Newton meters divided by meters gives you newtons. Last part, the coefficient of friction. This is sort of a review kind of thing. We're going to get the coefficient of friction out of F equals mu times N. Coefficient of kinetic friction because the puck is sliding. The friction force, I've got the answer from part B, the 0.239 of a Newton. The normal force would just equal the weight of the puck in this case. We've got 0.17 of a kilogram times 9.8. That comes out about 1.67 newtons. Normal force doesn't always equal an object's weight, but in this case it does because there's only two vertical forces, the normal force up and the weight down, and they have to balance each other because there's no vertical acceleration. So we've got the normal force, we've got the friction force from the previous part. Newtons over newtons cancels out. Friction coefficient is a dimensionless number. Power is the rate at which work is done. The formula, instead of saying it in words, P equals W over T. Focus. Got it. Let's say you've got a friend that weighs the same thing that you do, and you're both standing at the bottom of a flight of stairs. One of you decides to run up the stairs, the other one decides to walk up the stairs. By the time you've both reached the second floor, the same amount of work has been done. The same weight has been lifted to the same height. But the one who ran up the stairs did the work more rapidly. So that's more power, okay? Same work, more power, because the work was done more rapidly. Alternate formula. This one here is the basic definition. You know, this is what defines what the word power means in the first place. From that, it's possible to show that power is equal to force times velocity. The little subscript there, there's supposed to be two little parallel lines, the parallel component of the force. It's the same story as work. Remember, work is the component of the force parallel to the direction of motion times the distance, F cosine theta S. Same thing here, the component of the force parallel to the motion, F cosine theta times V. And I've lifted it too high. See how you like that. That looks good. So this applies to anything. This is a more specialized equation for mechanics problems. I mean, when in the spring semester, when I'm talking about electrical power, we'll start with this again. And from there, you can get a specialized formula for power that involves voltage and current. And this is useful for mechanical types of situations. Like this explains why heavy trucks go up steep hills slowly. If you're driving along in your car and you come to a steep hill, most cars have a lot of reserve capacity in the engine, and you just push down further on the gas pedal and you zip right up the hill. If you're driving a semi with the trailer stacked right up to the top of, you know, pretty much right there at the legal limit, or maybe even a little more, what you're supposed to be hauling, you don't have a lot of reserve capacity in your engine. So, you know, just to simplify the situation a little bit and say that you've got just a constant amount of power available. If the force gets bigger because it takes more force to pull you up a hill than it does to run on the level, if F gets bigger, V has to get smaller to still multiply out to the same amount of power. And that's why you sometimes are going along the thruway and you see the semis with the flashers going because they're under 40 miles an hour. This is good for explaining that sort of thing. It's not good for, you know, talking about the power given off by a light bulb, unless you want to look at it from a mechanical point of view and talk about the force and the velocity of the electrons going through the light bulb. But anyhow, units to measure all of this in. Work is measured in joules, time is measured in seconds. A joule per second is called a watt. After James Watt, who didn't exactly invent the steam engine, but played a really important role in developing it anyhow. If you're measuring in traditional units instead of the SI system, work is measured in foot-pounds and time is measured in seconds. The British system, the old British system with its characteristic charm, does not give a special name to 1 foot-pound per second. Well, that would be like having 10 inches in a foot or something sensible like that. Rather, 550 foot-pounds per second is given a name of its own. It's called a horsepower. There is nothing inherently mechanical about measuring power in horsepower. There is nothing inherently electrical about measuring power in watts. One's a metric unit, one's from the customary British system. It's like, what is your height in centimeters? What is your height in inches? It would be perfectly correct for you to walk into a hardware store and say to somebody, can you tell me which aisle I should be in? I want to buy a 1/10 of a horsepower light bulb. The reason you shouldn't do that is because the person will give you a funny look. But it's perfectly correct. A 1/10 of a horsepower is 75 watts. If you want a 75 watt bulb, it's a 1/10 of a horsepower. We'll round it off a little bit anyhow. So let's just do this one example and then we can call it a day for this recording. Although if you're really into it, you could probably keep going and watch the next one. So pause here, you can read it yourself. And now unpause and I will explain anything that you need explained about this. When I finish this recording, I've got to do some serious untangling of the cords on this camera. All this back and forth has got them pretty much tied up in knots. Anyhow, you can look at the question either way. You can start out with power equals work over time, or the other equation. This is the way I did it. power equals force times velocity. The question gives the power, 50 horsepower, and it gives the velocity, 1.5 meters per second. So the question gives you that, the question gives you that, and the question asks for the force. And that's pretty much all there is to it. So this is probably the more straightforward way to approach it. It's not quite all there is to it though, because the units have to match. Meters per second is an SI unit, horsepower is not. So, I mean, you could convert everything into feet and pounds and all of that and do it that way. I think it's probably a little more effort involved in that case, because if you work in metric units, you can just leave the velocity alone and not do anything with that. So I'm going to take the 50 horsepower and convert that into watts. You go to the formula sheet, there's that table of units on the last page. And you go down to the line that says power. And actually, I think I went one more decimal place with it on the formula sheet, but close enough. 746 watts is equal to 1 horsepower. $37,300 watts goes in for P, and the given speed for V. So comes out approximately 26,600 newtons. And that takes care of section 6. Yeah, I moved the computer and it swung the camera around. I don't know why they figure we need an eye wash station in this lab. There are no caustic chemicals. Unless somebody like sticks their finger in their eye and has something nasty on their finger. Anyhow, signing off.